Hello and welcome back to Building Integrity. I'm your host Josh Porter, and today we're going to be talking about Champlain Towers South, and we're going to be trying to answer the question, why did the rest of the building not fall? Now, immediately a bunch of you are going to jump up and say, oh, I know why, it's the shear wall, it's the elevator tower. But I'm going to take a quick moment in this video to explain why that's the case, okay, and how this works, and we're going to learn a little bit more about shear, uniform and non-uniform shearing, okay? But before we do that, I want to jump in and I want to show you some photos that was released recently by Senator Jason Pizzo, showing the site at Champlain Towers South. All of the debris, or the majority of the debris, has been removed, and you can see what you're looking at here in this photo is the garage slab with a little bit of standing water. Now, I've heard from someone at the site today, these photos were taken a couple days ago. I heard from somebody at the site today that actually this slab is now covered in salt water right now. But let's get into this and let's talk about what we can learn from these photos real quick. It's not the focus of this video, but there's a couple quick things we can talk about and learn. Okay, and here's another photo. This area here is showing the building that remained standing, which is what we're going to be talking about today. And that roughly covers that area there. And this is the base of the shear wall in this location here, okay? And from this photo, we can see the ramp. This is the part of the ramp that's still here. We generally see the column at the end of the ramp. If you go back and look at my video and watch that regarding what happened about 7 or 8 minutes before the building fell, and you're looking down into that parking garage, you remember that we identified this column and then the column beyond, okay? And then the debris and the rubble, which generally conforms to the planter area, was visible at approximately this location, okay? But the planter area itself actually extends from that column over to a couple more columns, right? And a little bit beyond. So that's generally the area of the planter boxes above. Now, we talked about in other videos as well is that the way this building collapsed, and looking at that collapse video, and we're going to watch that again in this video because we're going to talk about how it collapsed and why it collapsed in a progressive manner, and why the rest of the building didn't fall. They all go hand in hand with each other, dealing with the concepts of shear. But looking at this, we talked about those 3 columns. Well, these are your 3 columns that we're talking about. You can see them standing here, okay? So the question is, well, from looking at these photos that were released, what can we learn? What does this change? In all of our video series, we've been talking about various contributing factors and various possibilities. At no point do we want to try to hang our hat on any one type of hypothesis or say this is definitely what happened. But what we're doing is we're exploring hypotheses that have been proffered out there in the community and then testing those to see if they hold water and why they might make sense or not make sense. One of the things I think we can really probably rule out at this point is that there was a sinkhole under the building, at least any sinkhole of significant size. These photos don't show, any sort of giant gaping hole down here in the slab or anything that would have swallowed those columns and initiated the collapse. So I think we can take that away from these videos, or from this photo. We also see that there are no visible from the photo. Now, I'm giving this a little caveat here, a little asterisk, if you will, okay? There is no visible critical failure below the garage slab. Now, remember, we're talking about the initiating columns here, 1, 2, and 3. And it's either, on the garage level or the floor above or something around these columns. I'm not saying those columns specifically, but this is the general area. These are the 3 columns. That's the stack we see collapse first in the facade when it comes down, okay? And we can't see anything, but I will say say that with a caveat, is that we do have a lot of standing water around here, which makes it a little difficult to see what might be going on around column number 2, okay? So that might just be an optical illusion, and there may actually be some sort of depression in the slab here or hole or something that's just we can't really see, and perhaps that column buckled below grade. But I think at this point, we don't see a big mess, we don't see a big hole. So I'm going to say for now that we don't see any visible signs. That doesn't mean it didn't happen, it just means we don't see any visible signs that the failure was below the garage slab. Keep in mind that does not rule out that subsidence played a role at all. And so that brings us up to the third one. Subsidence as a stressor is not ruled out, okay? And the reason why I say that is because if subsidence typically leads to what's called differential settlement, so the parts of the building settle at different rates, which can cause a lot of internal stresses. Now, it may not be the thing that causes the collapse of the building, but it may be the thing that allowed it to collapse because the building was already under various stresses, okay? All right, so we're gonna go back and we're gonna watch this facade collapse because this is gonna be very important for the rest of this video. So we're gonna watch this together again and then we're gonna go on. All right, so you can see that very front face goes first, then it goes deeper into the building, and then the the east facade then leans a little bit before pancaking in on itself. Okay, so what we're talking about here is we're talking about the structure that, first part of this video, we're gonna be talking about the structure that didn't fall, the part of the structure that did not fall. So we can see this in this photo, and what we're gonna be talking about, one of the main reasons why this building did not fall is because of this shear wall here, okay? And this shear wall is reinforced solid concrete from the piling cap all the way up to just below the roof, okay? It's very strong, it's very stiff, it's very rigid. Now, it's not incredibly strong compared to today's way that we might build a shear wall, but in relation to the rest of the building, it is a very, very strong, very well reinforced wall. And you can see that at every level, that slab was integral into that wall. So they would pour the slab, and it would go into the wall, and then they would pour the next layer of wall, and then so on and so forth. So the slab at this portion of the building was very much tied into this shear wall reinforcement, and of course the concrete pours themselves. And you can see that with the lighter colored lines here at each slab level. Okay, so zooming in, what I want to talk about is this facade. Okay, we know the facade. I'm just going to kind of quickly draw sort of the front of the building. And then you've got, your slab at each level. And then you would have columns. I'm just going to draw them as sticks for speed's sake here. All right. And so what we know is that, or what we can tell from the video, if you want to go back and watch the video several times, just rewind this video and you can watch it a couple times. But we know that this front starts falling first, and then this next part starts falling, and this next part, and this next part, until eventually the back of the building fell. So you can see that this part of the building was ahead, the facade here was ahead of the rest of the building from collapsing. Well, why is that important? Well, the reason why that's important is because that's going to create an immense amount of shear force right here at the leading edge where that slab connects to the shear wall, okay? And normally when we're talking about shear and when we're modeling it on paper as engineers and drafting and designing these things, most of the times when most engineers are designing these buildings, we are thinking in terms of uniform shear. Is there enough shear strength in my structure across this entire slab, right, to prevent this portion of slab, maybe right here, to prevent this portion from collapsing? And so on paper, we're saying, oh, well, that's plenty of shear, that's great, that's wonderful. But in reality, and in the way this building actually collapsed in a progressive manner, because the facade started coming down first, all of the shear force of that facade was put right at the leading edge. And so what I wanted to talk about is, and I have some videos to kind of show you an example of why this is important. Because if you can imagine yourself holding a piece of construction paper and just trying to wrench it or tear it apart, it's going to be difficult, and it's going to be difficult to tear it apart in a nice straight line. But if you can imagine that this portion here is rigid, so like this portion here is your shear wall that's in the building, okay? And it's a very rigid, doesn't want to deflect, has a lot of concrete, has a lot of reinforcement in it, and this is your shear wall. And then this, now in this video, the person is tearing up, but just imagine it going backwards as the building is tearing down, okay? And watch what happens when you create a rigid face along this leading edge, and what happens to the paper when it tears. So the paper, not only does it tear straight, but the paper actually tore. The paper actually tore very, very easily. And because when you're pulling up on the paper at this edge, instead of trying to grip the whole paper as a whole, instead of doing that, you grab the leading edge. All of that lifting force is concentrated right here at the leading edge of those fibers, okay? And so it's very easy to tear that fiber, okay? You gotta imagine these as little fibers connecting the sheet of paper together, like stitches almost. So it's very easy to break one fiber at a time as opposed to trying to do multiple fibers all at once. Okay. So where is that shear wall in relation to the rest of the building? I wanted to use this photo to orient you guys. It's a great photo from the Department of Transportation that I got. So the shear wall in relationship to the rest of the building is located right here, and it terminates right there. It goes underneath the mechanical room for the elevators. All right, and so what happens is that this, think of this like the last video you just saw with the ruler and the construction paper tearing. This is your leading edge of your collapsed portion of the building, okay? And it has a downward motion, unlike the paper video where it has an upward motion, but that really is insignificant. But it has a downward motion, and you can see that the concrete and steel, this building didn't have to rip this entire section of concrete at once. It only had to start tearing at the leading edge right here. Okay, and so that is partly why this remaining, that's part of the explanation of why this building remained during the collapse, is because this building over here, the portion that collapsed, was able to do so in a manner in which it only put minimal stress on the remaining building as it proceeded down the line of this shear wall. Okay, so looking at this again, I'll go back to one other thing too. When this building tore, if what we're saying is correct, so you have this very rigid shear wall right here, right? So here's your shear wall. All right, now if that's rigid and you're going to rip the building down, every floor is like a sheet of construction paper from that video. Every floor is going to rip down starting at the leading edge right in here, okay? And if this building's going to rip down and you run out of shear wall right here, okay, what would we expect that slab to do? What would we expect that construction paper to do, if you will? Well, we already know what actually happened because you can go back and look at photos. What we know happened is that this building tore along the face of the shear wall, and then it ripped sideways and came right between these two racks of AC units, okay? And this AC mechanical equipment here actually fell down with the rest of the building because it's on a large rack, which is partially over that break. Okay. So looking at this photo here, why did it rip in that way? So following the direction, I'm going to take the next floor down because it's easier to see. Following the direction of this slab, okay, we can see that this doesn't quite line up with this. All right, so there's got to be a jog over here, which happens to go like this. And it's a little hard to see in the debris. This is why I want you to focus on the slab out here, okay, while I'm talking about it, because it's the same plane, it's the same level as this slab here that I'm talking about, okay? So it rips this way and it goes that way. Well, why did it stop in that manner? Why did it rip in that manner? Why didn't it just keep ripping through the building this way? Well, that's because it had already started this sort of tearing motion where it's tearing from one side and shearing down, using the paper as an example, individual fibers at a time, if you will. But it's breaking the concrete interface, and it's breaking the rebar one at a time as it goes down. So it didn't have to deal with the whole structure as a whole. Well, once that motion has already begun, the only thing you needed to stop this thing from tearing any further was to have some sort of rigidity built into the slab system to stop that. And so what we have here is we actually have the column on the perimeter of the building, and you can't see it, but you have another set of columns in here. And so what it ended up doing is it ended up stopping at the column line, and it lines up perfectly with that, which I'll show you. And to show you an example, a visual example of this tearing angular action, we took another video and I'll show you what that looks like here. All right, so here is the same idea. You have your building, you have your retaining wall, or I'm sorry, your shear wall, if you will. All right, so there's your shear wall. Where the shear wall runs out, the slab is able to, or in this case, the construction paper takes an angular motion, okay? Depending on, and in this case, it was depending on the way the person gripped it who recorded this. But then eventually you're gonna hit that column line, and then it's going to rip down that straight away. We can see that when we look at the construction drawings. This is the color-coded plan that we had come up with a couple weeks ago. It's been slightly modified, but this generally shows you that the red area was generally the first area to go down. This area was the second. This area was the third, and the fourth remained until it was demoed. All right, so here is this retaining wall. I'm sorry, I keep calling it retaining wall. I mean the shear wall. So here's the shear wall. There are retaining walls in this drawing, and I was just studying them right before I started recording this video, so my tongue keeps slipping into calling them retaining walls. So here's the shear wall. And here is that column line I was talking about. Here's a column, here's a column, here's a column, and it lines up right with the center of that balcony, which is what we saw in the previous photo. And so essentially the building tore this way and then hit the reinforcement and the additional slight strength that was in that portion of the slab, and then went ahead and followed the column line down. That is essentially why this building remained, was because the shear wall initiated, instead of initiating a collapse in this direction, it was able to resist it long enough to convert the energy of the collapse from a total catastrophic distribution of energy into a shearing motion where it just started at one end and started ripping down the face of that shear wall. And you can see, zooming in, just how much this profile actually matches what I'm talking about on the drawing. Okay, so it's essentially the same principle that happened. Each layer of this of the slab was essentially a flat plate, so you can think of it as just a very strong sheet of paper, and it will follow essentially the same principles. Now, I understand there's a lot of other columns in this, and there's a lot of other things going on. There would have to be punching shear failures. There would have to be a lot of other things that go on, which we'll talk about maybe later or in this video, but maybe more in depth in a future video. But essentially, this is what's happening. Why didn't most of the forces that are going to transfer, for example, this column can't really transfer forces to this column, right? It has to use the slab to transfer these collapsing forces. So, however, this column failed is still something left to be investigated. Deeper into the building, we know it's progressive, and I'm going to explain to you a little bit about how that can happen. But we're not 100% sure on how this happens yet, right? But clearly, in order to do this, in order to transfer any sort of collapsing motion from this column over to this column, you have to use the slab to do that. And this shearing action is what prevented this building, this side over here, the fourth section, from actually falling. So going back into this video, or into this photo, I wanted to kind of just quickly draw what that would kind of look like. So instead of your slab being up here at the first initiation, it would be down here, and it would kind of curl up like this. And that's essentially what we're talking about. Every slab was falling in this same motion as we go down. Okay, and the next slab would have been down here, and it would have had this type of action. And so you can see that the shear was greatest here where it already tore, and then it's just tearing like a sheet of paper down the side of that shear wall. Okay. So now I want to talk about how one of the mechanisms that contributes to progressive collapse. What we still don't know, and what we won't know for probably a long while, is what caused the facade, the front of this building, okay? What caused this to begin? What caused it to initiate collapse? I'm not addressing that in this video. I haven't really postulated a theory on that at this point. But we do know that there are several things that are interacting to have created this. or contributed to this. We talked about the punching shear issue at the pool deck slab in the last video. That's a contributing factor, but that alone probably can't stand up as a sole contributing factor, as the only cause that caused the building to collapse. Okay, but how does this collapse cause the next column to collapse, right? And so what I want to do is I want to show you one of the pictures that I showed you in the last video, which was an example of punching shear. We talked about the shear heads and how this looks different, how most punching shear sites from the past, from historical records, look different than the columns that were poking through the pool slab there. But I want to show you that this portion of slab is still supported and attached by this column. And there are two interesting things to look at in this column, or in this configuration. One is the angle between these two. This is not a 90-degree angle anymore. So this slab used to sit like this, okay? And we would call that a 90-degree angle. All right, this is tighter than a 90-degree angle. So what's happening is, you can't see it because it's behind there, but essentially that slab is angled like this, and that punching head looks something like that, and the column's under distress like this. So it's going to be sticking out. You just can't see that sticking out portion. And so just like the sheet of paper, like we were talking about before, you can see that once a slab collapse is initiated, as it kind of comes down and it approaches each column at an angle, it's not shearing the whole thing at once. It actually is shearing this leading edge first, and then the rest of it punches through the slab. So I'll draw another picture of that to maybe make it a little bit clearer. So you have your slab, and then you have your column supporting the slab. And in the last video, we talked about punching shear in general, which mostly relies on the concrete shear strength, which I wish I'd pointed out a little bit better in the last video. But it does also, now mathematically engineers don't rely on the steel, but realistically, if there's steel in here, it's going to contribute, okay? That's just a matter of fact. But we typically, when we calculate punching shear, we don't rely on that conventional reinforcement in the slab for our calculations. Now, the idea is, and when we calculate this per code and based on lab tests and stuff like that, the idea is that you have to overcome a shear strength equal to this entire area. And essentially what the formula implies in the engineering code books is that that entire face all the way around the column capital, or around the column shear head there, is going to contribute to shear resistance, right? But let's say you have a multiple column configuration, okay? And you have a continuous slab over these columns. All right, and then let's say the slab collapses over one of the columns first. And as it hasn't collapsed on this column yet, and I'm exaggerating obviously the angles and stuff, but you can see that this is not going to shear through uniformly, okay? It's actually going to have greater pressure at the leading edge than it does at the trailing edge. And so this is how a building that is a plate slab construction progressive, I should say a building, but I should say this building, the Surfside building, this is how the progressive collapse occurs. You have to have some sort of initiating event which causes some sort of failure in the structure. Maybe that failure was further down, and we still, you know, like I said, we still don't know exactly what was the exact initiating cause of the collapse. But once it begins to collapse and the slab starts collapsing, two things are going to happen. One is you're going to have a bit of catenary action, which is the fact that this slab, let's say it's just this one failed, this slab is sort of sagging, okay? And just like two people holding a jump rope, if somebody really heavy were to try to jump on the jump rope, it's going to pull those two people into the center. And so what that does is this action of the slab falling actually pulls that column over. And you can actually see that in this one right here. You can see how this column is not straight up and down anymore, but it has actually been pulled over by the slab, right? So in the same way, our columns would be pulled over. But then also the other thing that's happening is you have this shearing, this non-uniform shearing occurring at the column capital. And so as this slab then collapses around this column, okay, and it reaches the next column, looks like my slab got crazy there. All right, sorry about that. All right, and then as this reaches the next column, you can see that this column, again, is not uniformly bearing. This slab is not uniformly bearing on the column, and so therefore you're going to have excessive load there, and you're going to have less load here. And so your punching shear, this thing is going to punch through like this. Okay? And so what I'm getting at is, while this column may have been perfectly calculated to resist punching shear inside the building, we can reasonably assume that there was no corrosion damage, no issues to the rebar, nothing going on, no top slab delamination. But once this process begins and this slab starts collapsing in this way, all it's got to do is just break this leading edge, get the leading edge of shear to start occurring at that column, and then the rest of it will follow suit. Okay, so hopefully you guys learned a little bit about shear, about why the portion of the building that was still remaining didn't collapse. Thank God for that portion at least. And hopefully you guys learned a little bit also how this non-uniform shearing action contributes and can lead to progressive collapse of a plate slab construction building. Well, that'll do it for this video. I appreciate you guys watching. Take care.